Welcome to a lesson on probability, and of course we're going to say that probability rules, and that's true. You never know what's going to happen, but probability can help you find the answers as long as you remember the rules. So let's make sure we've got all the rules for calculating probability under our hat. As well as that, we want to ask some big questions about how this section of mathematics can help us in our everyday lives. So let's go and have a look at some of those questions. The first one is it possible to use maths to predict the future? Is it possible to find the chance of one or even two different events occurring? Well, fortunately, the probability rules help us with exactly that idea. It might not be able to tell us definitely what's going to happen tomorrow, but it will give us an idea of the chance of whether something can happen or won't happen on a particular date. So let's get a big picture idea by going through a concept map of all you need to know about probability. So in our concept map here, we're going to be covering certain things. We're going to be looking at the idea of theoretical probability. We're going to be looking at the idea of what is a sample space and how we can represent that sample space into different events or different sets, which we call Venn diagrams. In terms of the Venn diagram, we also introduce the word complement. We'll discuss a little bit about that. When we're considering two or maybe even more events, we have this terminology of that the events could have an intersection or they could have a union. And then there's this very interesting idea of something being called mutually exclusive. So when we have a look at this big concept map, the big overview, I hope you can see there are different parts. But what's really important is that you get the terminology and you get the ideas that come from really the most simple thing about probability. So let's get started by looking at some of these rules and some of these terms that you're going to need to become very familiar with. So the first thing that we're going to look at is the idea of a sample space. A sample space is a collection of events or outcomes in an experiment. So when we do probability calculations, we usually do experiments. And when we say all of those things, all of those outcomes or events, they're part of the sample space, we write that sample space as S. When we want to know the number of events, then we're going to write it as NS, just like that. So I hope you can see that the sample space covers many possibilities. In fact, it covers all of the things that we're looking at. But how do you think we could represent that graphically? Some people don't like the little numbers and the N brackets S. Is there a way that we can visualize what the sample space looks like? Well, absolutely there is. Let's have a look at it. And here we have, representing the sample space, we've drawn a rectangle, and inside the sample space, there could be a whole number of different events, different things taking place, and that is encompassing the things that we're examining. So within the sample space, we can now put into it things that we would like to happen, that we don't want to happen, and we could represent within the sample space a circle or a Venn diagram. A Venn diagram is represented as a circle, but it really is just a set. It could be a set of numbers, it could be a set of games, it could be a set of sports, but it's a list of things that we would put into a particular grouping. Only remember that it is part of the sample space. And so again, when we look at it, we recognize that it contains certain elements, only some, or events, and we denote it with a letter X or A or B or whatever. If we want to know the number of those events or outcomes in a set, we say it's the number N in brackets X. And to represent it graphically, there we go. We've got this is the set. It's the Venn diagram that we're looking at. The Venn diagram of those outcomes or those events that are part of the sample space. So we recognize that it is not overtaking the sample space, it's within the sample space. Now, if we go on and we say, so what's this idea of probability? How does this set, this Venn diagram of X events, the ones that we would like to happen, fit into all of the possible events that are represented in the sample space? Well, the theoretical probability is easy to calculate. All we've got to do is we've got to count the number of times a particular outcome or event takes place, and then divide it by the total number of events in the sample space. So we get this idea that the number of favorable events, the ones that we would like to happen or we're interested in happening, is divided by the total number of events. And so the probability of X taking place is simply this fraction. It's the number divided by the total number in the sample space. Just to be aware that this can be represented as a percentage, it can be represented as a fraction, and that could be a common fraction. So it could be something like 1/5, or it could be represented as a decimal fraction, or it could even be represented as a ratio, something like 1:5. All of those are possible representations of probability. And so if we recognize that, there's another key thing that I want you to recognize, and that is, what's the probability of the sample space? Well, it's the number in the sample space divided by the total number in the sample space, and that comes out to 1. Now, guys, that's a very important rule, and it's a very important conclusion that we must remember, that if something is certain, we're going to take something from the sample space and we say, what's the probability of this thing happening? Well, it has to be certain. It has to be certain because it's in the sample space. The total number of things in the sample space divided by the total number of things in the sample space, it's 1. A percentage of 1 is 100. That tells us if the probability of something happening is 100%, we know it's certain. Of course, if the probability of something happening is 0, what do you think that tells us? Well, it's never going to happen. It's like, what's the probability of, finding a unicorn? Well, we don't want to disappoint too many people, but we'd recognize that in terms of what we currently know, the possibility or the probability of finding a unicorn is there's no chance. Of all the animals on the earth that we know about, there's not one unicorn. So we'd have to recognize it's never going to happen. The probability is 0. So there are 2 extremes in probability. 0, not going to happen. Definitely going to happen, it's 1. All the other probabilities lie between 0 and 1. So we can have a probability of 0.5 or 50%. That tells you it's a 50% chance of happening or a 50% chance of not happening. It's even. But if the probability was 0.8, then it's more likely to take place. If the probability was 0.2, it's less likely to take place. I hope you've got those big ideas about what theoretical probability is about. But now we have to link to reality. Theoretical things don't always match what's happening in reality. So you might want to say, well, I'll take my probability tools and I'll go to the casino and I'll win lots of money. Well, you might not. You might have a problem because, you see, probability only works when there's a very large number of data. And if we are going to do experiments in probability and we do a number of trials, we get something called relative frequency. These come from doing games or things like tossing a coin or rolling a dice over and over and over again. And if we do that, we'll find if we do enough of them, then the relative frequency matches the probability. But you have to do thousands of them to get very close. So let's just define that relative frequency idea. So if we're doing real experiments, We recognize that the relative frequency is calculated by the number of favorable events or outcomes that we're looking for divided by the total number of trials. And a trial is just something that you're going to do. And we write it like this: it's the number of things that we're looking for divided by the total number of attempts that we're going to do it in. Here's a new word: complement of a set. The complement of a set includes all the elements of the sample space that are not in X. So the complement of X is written as X with a little dash or prime on it. So let's have a look at that visually. So in this case, we've got the sample space with X on it, the Venn diagram of X. Now look what happens. All the blue represent the elements that are not in X. They make up the complement of X. So everything in blue belongs to the set that is the complement of X. Now, we have some rules about the complement. We can say, what's the number in the complement? Well, we can say the number in the complement is the number that isn't in X. Well, what does that mean? Well, it means it's the number in the sample space minus the number in X. And if we were to look at probability, then we'd recognize the probability of the complement is going to be the probability of the sample space. Remember, it's the number in the sample space. It's the probability in the sample space minus the probability of X. And we know the probability of the sample space is 1, so we can get the probability of the complement is 1 minus the probability of X. Now, this is a very useful rule, and I want you to make sure that you've got it very clear, because we're going to show how we can use this in some applications of the rule a little later on. Let's get on to our last two rules, which are about the union and intersection. So here we go. And what we recognize is that in a union, we've got, it is the interaction that contains all the elements of the set of at least one of all the sets together. So the elements that are in at least one of the sets. And we write it as X union Y, or we say X or Y. Now, this is quite important. You recognize here we've got the purple box representing X union Y. They can be in X or in Y, and only in X or Y. When we go on, we recognize there's an intersection when they overlap, and we write it with this U formation, and they must be in both sets. Now, what's important here is if something is in the intersection, we only count it once. Even though it belongs in the particular set, like say X, and it belongs in Y, we only count it once because it's part of the intersection. When we get this, we recognize that in this case, you can see the overlap is here. The intersection is not equal to 0. But we can have a situation like this one, where the intersection, there is no overlap. The intersection is equal to 0. When this happens, we say that these events or sets are mutually exclusive. They cannot happen at the same time. The intersection is 0. And so we can represent it like that, as we've seen. And when we calculate the probability for mutually exclusive sets, we recognize the probability of X or Y happening is equal to the probability of X plus the probability of Y. We call this the OR rule. And I think that's enough of rules for the moment. We're going to investigate some more rules, but I think it's time to take a short break.